Standard 17 is all about replacement reactions. When we talk about replacement reactions, what we're talking about is one atom or element replacing another in a compound. And so in order to look at replacement reactions, we have to go back and review some of the concepts that we've already seen before. Specifically, replacement oftentimes comes down to the idea of electronegativity. So if you remember, electronegativity is the idea of how closely attracted the valence electrons or outer electrons in an atom are to the nucleus. Okay, so we look at the nucleus, and if a nucleus has a lot of protons, that means there's going to be a lot of attraction to valence electrons. However, if there are a lot of shielding electrons on those inside energy levels, those electrons are going to shield the nucleus from the valence electrons and cause a little bit of a weaker attraction. Okay, so we looked at this specifically in the case of metals, and looking at the fact that sodium, for example, has a lot of shielding electrons on levels 1 and 2, but only has one valence electron on level 3. Okay, and so since sodium has a limited number of protons, most of those protons, 11 protons, are going to be balanced out by the 10 shielding electrons, which means that this outer valence electron is not going to have a very strong pull to the nucleus, which means that sodium can very easily lose an electron and form a positive cation. Now, we talked about this in the context of nonmetals and looking at how valence electrons are given from metals to nonmetals. But what happens when you get two metals together and one's an ion and one's not? Well, if we look at zinc and copper in this case, this particular zinc has all of its valence electrons. It has a zero oxidation state. And copper, if you take a copper ion with a +2 oxidation state and you mix it together with the zinc, what you'll actually see is that the zinc will give 2 valence electrons to copper. Well, how can this be? Metals aren't electron acceptors in most cases, and you'll never really see a metal, at least in this class, with a negative charge. But when we look at zinc and copper, if we compare those two things, copper's valence electrons have a stronger pull towards the nucleus, or a higher electronegativity, than zinc's do, which means zinc is less electronegative, has a lower ionization energy, and can more easily give away 2 electrons. So even though copper doesn't really want its valence electrons, it still is better at stabilizing them than zinc is, so it'll take zinc's. So we can organize these metals in order of which metals are going to be least likely to take electrons and which metals will be most likely in what we call the activity series of metals. Okay, so looking at this list here, we've got potassium at the top and gold on the bottom, which means that potassium is the least electronegative and the most likely to have a positive charge, whereas gold is the most likely to accept electrons from other metals, if those other metals or if gold is a cation. Okay, now you'll notice that not every element is in this list, but it's enough for us to be practical. So what this means is that in a single replacement reaction where we take an ionic compound with, say, cation B, whatever metal B is bonded to some anion, could be a nonmetal element, could be a polyatomic ion, doesn't really matter. But the point is that in a single replacement reaction, another metal will replace metal B in this compound, so that we would wind up with B being all by itself and A being bonded to that anion. So, for example, if we look at the reaction between iron and copper 2 sulfate, which we have already done in class, iron with a 0 oxidation state still has all of its valence electrons, is higher on the list than copper is, which means iron is more reactive. Okay, it's better at giving away its electrons than copper is. Copper is more likely to stabilize those valence electrons. So iron will give valence electrons to copper, which will cause it to lose this +2 charge, this +2 oxidation state. And if it loses that +2 oxidation state, then it no longer has any attraction to sulfate ions. Okay, but in the process, iron giving away 2 electrons means that iron will have a +2 oxidation state, making it very attracted to those sulfates. Another good example of that would be sodium and zinc sulfate. Okay, so sodium again is higher on the list than zinc is. So sodium will give its valence electrons to zinc, and you'll wind up with sodium sulfate, it should be Na2SO4, and Zn. But what about if you try to react a metal, like say iron, with something that's higher on the list? Okay, so if we look at the relationship between iron and zinc on the activity series, we see that iron is lower than zinc, which means that zinc is more reactive. And the general rule is that the more reactive metal, the metal that's higher on the list, will always end up bonded with the anion, which means that since zinc is higher on the list than iron, iron won't be capable of giving electrons to zinc, which means that this compound is going to stay exactly as it is, and you're not going to have any reaction. In order for there to be a reaction with zinc sulfate, you need to have something higher on the list replace the zinc. Otherwise, no reaction will occur. So that was single replacement reactions, and we can expand this a little bit further into double replacement reactions, where instead of one thing displacing another, we see two partners swapping places. Like in this general equation up here, where if you have A bonded to B and C bonded to D, A and C, assuming those are both cations, are going to switch places so that A winds up bonded to D, forming this compound. Okay, so cation A and anion D bond together, and C winds up switching over to be with B, so that cation C is with anion B. So for example, barium chloride and magnesium sulfate can react to form barium sulfate and magnesium chloride. And all that's happened is the metal cations have swapped partners. And again, this can happen with either polyatomic ions or elemental ions. And most of the time we do this in water. Most double replacement reactions occur in water is how we think about them. So you'll pretty much always see these as aqueous solutions. And one of the big things to remember about ionic compounds that dissolve in water is that they dissociate. Okay, when they dissolve, they completely separate from each other. So your cations will be surrounded by water, your anions will be surrounded by water molecules, but these two things will no longer be really bonded with each other. So assuming that our barium chloride and magnesium sulfate are both dissolved in water, we could actually separate these ions out since they completely dissociate with each other and describe the reactant side of this equation as being a big jumble of aqueous ions, where we have barium ions, chloride ions, magnesium ions, and sulfate ions all in aqueous solutions. But if we look at the end of this reaction, okay, we notice that barium sulfate is actually a solid. So why did that happen? The thing is, not all ionic compounds are dissolved in water. Okay, not all ions are soluble. And so there's a list of solubility rules that we'll be looking at in more detail in class that dictates whether or not things can dissolve. And in general, the solubility list, and this is the same one you'll be given on the final exam, the solubility rules follow based on the anion. So if we look at the anion in this compound, sulfate, SO4, we can look for sulfate on the list, and we can say all sulfates are soluble. They fall under the soluble category, which means they dissolve, except for when they're bonded to calcium, strontium, barium, mercury, lead 2, and silver. Now in this case, the sulfate is bonded to barium, which means it will no longer be soluble. It will actually be insoluble. It will not dissolve, and it will form a solid. And we call that solid a precipitate. Okay, that solid will settle to the bottom of your solution and not dissolve. Okay. Magnesium and chlorine, on the other hand, magnesium chloride, it says all chlorides, bromides, and iodides are soluble except for silver, lead, and mercury. Now, this chlorine is not bonded to silver, lead, or mercury, so it will dissolve, and those aqueous ions just stay dissolved in solution. So what happens to those ions? If we look closely at these reactions, those ions will actually stay dissolved, and nothing will really happen with them. So let's say, for example, we take this reaction between sodium chloride and silver nitrate, forming sodium nitrate and silver chloride. Again, the sodium and the silver just kind of swap partners here. And checking the solubility rules on the previous slide, you would notice that silver chloride would be insoluble. It would not dissolve, and it will form a solid, whereas sodium nitrate would dissolve. Okay, so looking at these compounds, we can see that sodium, chlorine, silver, nitrate, all on the reactant side of the equation, again, all aqueous ions, all dissolved in solution. Okay, but when they react and when we combine those two solutions, the silver and the chlorine will stick together and no longer be capable of being dissolved, and they will form a solid that sits at the bottom. Okay, and the sodium and nitrate, on the other hand, since they do dissolve, they form an aqueous solution, will stay dissolved in that solution. Now, these sodium and nitrate ions are what we call spectator ions. If you look closely, they don't really change at all in this reaction. Even though we express them as being a new compound, in reality, the sodium and the nitrate start off as just dissolved ions and end as dissolved ions. There's nothing really happening to those atoms, okay? And so when we write equations for describing what's really happening here, we can actually eliminate the spectator ions. We can take the spectator ions, sodium and nitrate, out of the equation completely, since they start off as dissolved ions and end as dissolved ions, and we can write what's called a net ionic equation. And in the net ionic equation, we're simply expressing exactly what's truly going on here, okay, what things are actually changing, eliminating the spectator ions that stay dissolved. Okay, and so looking at this one, what's really happening is you're forming silver chloride out of chloride and silver ions. And there's nothing really else going on there. They start as dissolved ions, form a solid. So you'll notice that these things kind of look a lot more like a synthesis reaction than a double replacement reaction, but it is still classified as double replacement. A special type of double replacement reaction is called a neutralization reaction, in which we can take an acid and a base. Now, we haven't talked about acids and bases yet, but an acid, and there are a couple different definitions, and we'll talk about another definition when we get into the pH standard, standard 18. But the first definition we're going to start with is the Bronsted-Lowry definition of acids and bases. And this definition simply says that an acid is defined as anything that gives away hydrogen ions, okay, H pluses. It is a hydrogen ion donor, and it has to be hydrogen ion. If it gives away sodium, not quite an acid. Okay, so anything that gives away hydrogen ions is an acid, and anything that takes those ions is considered a base. So looking at this reaction between HF and NH3, hydrofluoric acid, and ammonia, okay, looking at this reaction, you'll notice that the hydrogen leaves the fluorine to form a fluoride ion and bonds with the ammonia to form an ammonium ion, NH4. Okay, so this ammonium accepted the hydrogen, which made it a base. Now, one of the weird things about this is that when a base accepts a hydrogen atom, it actually becomes an acid, because you'll notice this is a double arrow between these things. And we haven't talked about double arrows yet, and those will be more in standard 19 about equilibrium, but the idea is that this reaction is reversible. It goes both ways, which means that hydrogen can go back onto the fluorine, which would make the ammonium an acid and the fluoride a base. Same thing with ammonia and water. In the case of water, water gives hydrogen ions to ammonia, which makes water actually an acid, which is kind of strange. And ammonia, again, being a base because it takes hydrogen. But this base, this ammonia, when it becomes ammonium, becomes what we call a conjugate acid. Okay, so the base has become an acid because it can give that hydrogen ion back to the hydroxide, this polyatomic ion here. And so the water, where it started as an acid, a proton, or a hydrogen atom donor, became a conjugate base. And one of the very important reactions that we'll deal with a lot more in standard 17, a good net ionic equation that we'll use very often is hydrogen ions reacting with hydroxide to form water. And we'll deal with that one a lot more in the future. So the last thing to differentiate between is the difference between strong and weak acids. Now, once again, when ionic compounds and compounds dissolve in water, and when acids dissolve in water, the hydrogen ions will dissociate or separate away from the parent ion. Okay, and a strong acid will do that very well. It has a very high degree of dissociation, is what we would call it. Okay, but weak acids are defined as those that don't do that very easily. Okay, so the hydrogen ions don't always separate from the actual thing that it's attached to, which makes it a very weak acid. It's not very strong. And so we can compare these things. The American Chemical Society uses this analogy. Imagine an army in which some of the soldiers are capable of drawing their swords. If you have a highly concentrated army or a concentrated acid, and that acid is strong, you will have a lot of soldiers who are all able to draw their swords. However, having a highly concentrated weak acid means you have a lot of soldiers or a lot of acid molecules, but not all of them are capable of actually drawing their swords. Some of them are stuck, okay? Same thing with the hydrogens. Not all of them are giving away hydrogens. Dilute acids, acids with not a very high concentration, that are strong will still have just as many hydrogen ions giving away. And dilute and weak acids are the weakest of them all.